Hi guys, and welcome to our Module 3 lecture series. Our first part of our lecture is going to be on percentiles. So we've kind of already talked about percentiles a little bit in our previous module, and we referred to them by means of z-scores. So if you recall, we have a raw score of interest. We can look at that within our distribution under a normal assumption, or an assumption that we have a normal distribution. And then we can find the z-score that is associated with that raw score. Now remember, when we use z-scores to create percentiles or to estimate probabilities, they are estimated, okay, because we are under the assumption that we have a normal distribution. Now, we know that our samples are not always perfectly symmetrical and normally distributed, so we have other methods of calculating percentiles, and that's majorly what we're, or primarily what we're talking about within this lecture. So, just to kind of recap on what percentiles are, the book definition is a point or position on a continuous scale of 100 theoretical divisions such that a fraction of the population of a raw score lies at or below that point. So the point or position is our raw score of interest. Percentages can range from 0 to 100, so that's our continuous scale of 100 theoretical divisions. And the fraction of the population that lies at or below the raw score of interest is what is known as our percentile. So percentiles are a nice way to standardize measurements. They're also referred to as a type of standard score, which is going to help allow us to compare or evaluate raw scores that maybe have different units of measurement, or maybe they come from different populations. Okay, so I like to use visual representations of like comparing an apple to an orange. These are two different fruits, right? So you could look at it as the apple is one population, the orange is another population, and then we can compare them using a percentile or a normalized or standardized value. Because instead of being on different scales in terms of the sample or where the sample was collected from, they're still standardized to a scale from 0 to 100. I also love this GIF of this kid comparing cookies to each other, but generally that's what percentiles do. They're standard scores that allow for comparison on a scale from 0 to 100. As a side note, we've already talked about standard scores up to this point. They were all covered last week or in Module 2. So z-scores are a standard score. Remember, these are referred to in units of standard deviation or standard deviation units. So as in +1 or -1, +2, -2, +3, -3 standard deviations are equivalent to +1, -1, +2, -2, +3, -3 z-scores. Okay, again, a standard scale, we're not looking at the units of measurement. Rather, it is any way that you look at a z-score, it's the same, right? It's on a scale from -3 to +3. We can go past those values, but generally it's not really common. But the numbers on the scale are going to be the same for any type of measurement that you have collected, right? So long as you convert your original raw score to this standard score. The other standard scores we've talked about are z-score of skewness and z-score of kurtosis when we are evaluating distribution shape. And we've also talked about the coefficient of variation, which is one of our measures of variability. And that was when we could take the standard deviation and the mean of a given sample, so our descriptive statistics, and then we can figure out what the percentage of variability is within a certain variable. All of these are going to allow some degree of normalization, right? Again, so we're comparing measurements that maybe have different units. So in other words, we could say I want to compare different units of measurement that maybe we often use to assess health status, right? So I could look at someone's heart rate or blood pressure or their VO2 max. All of those variables have different measurements, but I can place them on a percentile scale, or I could put them into a z-score format, and that becomes a normalized value such that they all are on the same scale now. Okay. So that was side note. Back to percentiles and how they are interpreted. Okay, let's say that we have a person named Bob and he can do 40 push-ups. Okay, how good or bad is 40 push-ups? Okay, how good or bad is kind of dependent on the population that Bob falls in. Okay, so if Bob is a bodybuilder, this is a joke, Bob the Builder, okay, maybe 40 push-ups is equivalent to the 30th percentile. In other words, Bob is able to perform at or better than 30% of the population that he comes from, or 30% of the sample that he comes from. Okay, we can extend our sample to our population usually in these scenarios, but this is the general sense of how this works, okay? So in the context of being a bodybuilder, maybe Bob doing 40 push-ups isn't that great. But if Bob is a middle-aged man and he's, anywhere between the age of 40 and 55 years old, and maybe we collected a sample of 40 or 55-year-old people, or we know maybe the population mean and standard deviation for number of push-ups that middle-aged men can perform, maybe 40 push-ups is equivalent to the 94th percentile. In other words, Bob, our middle-aged man, is able to perform at or better than, right, 94% of the people that fall within his cohort. So we use percentiles to kind of better understand the value of a raw score within a data set in comparison to the known values from a given population or sample. And whether we're looking at population or sample is kind of just dependent on the data we're given. Sometimes you might know the population, sometimes you might not. It kind of depends on the size. We've looked at this figure before in last week's lecture, where we kind of more primarily focused on the shape of our normal distribution, our empirical rule, and how all of these percentages represent like the area under the curve in different areas. We also focused on our standard deviation notation, as well as, it's not on this one, but where our percentiles would fall. Percentiles are on this one. What's not on this one is the units of measurement, because this particular figure didn't have a specified unit of measurement. But this figure is relatively similar to the one we looked at last week. And you can see where percentiles are relatively associated with standard deviations from the mean. So at our mean, in a perfectly normal, perfectly symmetrical distribution, we would expect our mean to be equal to our median and our mode, right? So that means that our median is the value at the 50th percentile. So our mean should be aligned with that 50th percentile if we have a perfectly normal distribution. From there, you'll recall the empirical rule states that about 68% of our data lie between the first two standard deviations. And if we do some subtraction math here, we can see that we go from about 85%, which is more or less aligned with +1 standard deviation from the mean, and a 15, about 15%, which is more or less associated with -1 standard deviations or -1 standard deviations from the mean. So if we do 85 minus 15, about 70% approximately 68, right, is between the first standard deviation, okay? From there, if we kind of extend ourselves outwards, we're looking at about 95% of our data being in between +2 or -2 standard deviations. It's very, very rare that you're going to get somebody who's in the 99th, kind of like 98th, 99th percentile or above, and very rare to get somebody who is lower than the first percentile. So those areas kind of past 2 standard deviations are usually going to be considered where your outliers would be. Whether those outliers jeopardize your like mean calculations or whatnot is up in the air, but just know it's very, very rare for a random raw score to be pulled out and be recognized in these kind of outer regions of our distribution. But we're just kind of layering things together so you get a better idea of where these percentile numbers land within our normal curve. When we calculate percentiles, specifically for this lecture, we're going to be looking at exact percentiles. So going off of a set of data as is without assessing if it adheres to a normal curve or not. Okay, so the percentiles, again, are going to represent the percentage of values or observations that fall at or below a given point. Now, you'll recall last week that I said I use less than or equal to very, very loosely because it's not always the case. When you have a variable and you're using percentiles to evaluate the worth of your data, you need to determine, are larger numbers better or are larger numbers worse? And then based on how you have assessed that scale, that will then determine if you're actually looking at less than or equal to or greater than or equal to. But in general, I like to use at or worse than or at or below than a given point of interest, meaning that we're looking at the area at a raw score and the area to the left of that raw score, similar to z-scores. Okay. So the shaded area for an exact percentile is exactly the same as how we would evaluate the shaded area for a z-score. Just for an example of how we might put a percentile into words, if somebody had a raw score at the 85th percentile, that raw score is better than about 85% of the raw scores that lie within the sample and or the population. We can also say that 85% of all the values or observations are less than or equal to the given raw score. Again, less than or equal to is a very loosely used term here, and would be entirely dependent on the scale of the units of measurement that have been used. We can calculate percentiles for frequency distributions, which we've kind of constructed a little bit to this point. So we've looked at rank order distributions where we have values that are set in a certain order, usually in whole number fashion. Simple frequency distributions are very similarly constructed to rank order distributions, so I haven't really made that clear distinction in your activities up to this point. I usually merge them together because they're very similar. And we've also worked with grouped frequency distributions where we create levels of intervals that are separated by a standard size or standard interval size. So we'll look at how we can calculate percentiles for both of those types of frequency distributions. The important information that you need to know when you calculate a percentile is the score, the raw score, or ranking of interest, which we'll denote as X in all of our formulas. You also want to know the total number or set of scores, aka your sample size, which is denoted as N. Okay. For our solutions, again, in this lecture, from the formulas that we'll be using, these are how we calculate exact percentiles, within a given sample of data. Okay, z-scores again are estimated percentiles because they are under the assumption that you have a normally distributed sample, right? So when we use z-scores, a normally distributed sample has 50% of the sample on one side of the distribution and 50% of the sample on the other side of the distribution. When we calculate exact percentiles, we can't always make that assumption, especially if we're not testing for normality, in which case there may be some variation. Maybe you have 40% of your distribution on one side of your mean and 60% of your distribution on the other side of your mean, which is going to kind of skew the percentile that you calculate. So exact and estimated percentiles are not always going to be exactly the same.